Right, so thank you very much for inviting me to speak today. I previously did my PhD at Campbell School of Mines, now a research fellow in the university and research manager at Cornish Lithium. So I've been excited about mineral exploration in southwest England for the best part of 7 or 8 years now. And what I'm going to show you is the culmination of my PhD from a couple of years ago, which was largely based on mineral exploration using machine learning algorithms for tungsten. And I recognize a lot of names in the participants list today. So some of you may have seen this talk before, but it will be also looking more critically about the accuracy and bias that may be inherent in this model and what that actually means for the analysis. I just wanted to also acknowledge that this is a talk that has had contributions from many people, and they are all very much acknowledged at the bottom here. I couldn't have done it without them. So without further ado, so I just wanted to kind of cover what machine learning is, and this is more from sort of my perspective, having done a fair amount over the last few years. I've heard lots of terminology used to describe machine learning: non-statistics, statistics and computer science, pattern recognition, artificial intelligence or AI, and perhaps some less kind comments such as populist science or dirty statistics. Overall, I think personally, pattern recognition is the best term to describe machine learning as a whole, because ultimately what you're doing is you are leveraging the computational power of modern computers with the parallel processing of computer science. And you're looking at a hell of a lot of data, trying to find common patterns across all of those. And that might be something that you already know about, or it might be something that you are doing investigative work and trying to find the patterns that exist. I think it's worth mentioning, I think Jordan actually shared a similar news article title here. This is from a couple of years ago now, but machine learning is not causing a science crisis. This is one of the worst examples of reporting I've seen on the BBC Science page in recent years. It's actually down to people not understanding their data, not understanding the bias in their data, which is sort of a reflection of the title of this talk. And the other one is one that will certainly be still in the minds of people from last summer, is the idea of mutant algorithms. Quite frankly, they don't exist. And this is again an example of how people don't understand either the accuracy or the bias inherent in their data. And yes, some algorithms can start to teach themselves how to change, but it will still come out with the result based on the data, not its own decision-making process. It's data-driven all the time. I just wanted to kind of highlight the machine learning in geoscience can be done across so many different areas. And I'm not going to sort of read through all of these, but geochemical classification is kind of what Jordan's just touched on, and I'm going to focus on this prospectivity modeling idea. So before we dive in, just a disclaimer to say that if you do think of setting up an exploration company based on what you've seen today and you go bust, please don't come and sue me. And if you do find a mine, I'd be very happy to talk some more. One of the key things, and linking to Jordan's talk about what you need to do this, is a clear idea of your regional conceptual deposit model. And for Southwest England, I came up with something that looks like this. And this is perhaps part way towards this mineral systems idea that Jordan touched on. A mineral systems idea is trying to understand a known deposit and build up a bigger picture. So looking at, you'll often find the mine deposit at a local scale. You'll then try and look at it at the regional scale, which is what this is doing. And the next step would be to take that model and try and find similar regions across the world where you can see similar parameters, and then zoom back in to try and find that local scale and find those new deposits. This is sort of part way there, and perhaps is something that we could look at in southwest England as part of Deep Digital Cornwall as well, to build up this bigger mineral systems question. The main thrust of this sort of block diagram is that essentially we are looking for granite here in pink, and we're specifically looking for tungsten mineralization in this study, which is noted as these sheeted veins that cut the granite. We know that they're generally at the tops of these little tips of granite that stick up, and in 3D they might, you know, be at surface and come out at surface in like so. Oops. There's also some geochemistry involved here to identify the mineralization and the granite geochemistry and the aureole geochemistry, because sometimes we can't see the granite, sometimes it's buried, but the granite will have altered the rock slightly nearby when it's buried under below the surface. So that's useful to try and find deposits that perhaps don't crop out at depth, such as the deposit shown on the left of the model. And also we've included some structural data and some distance to our granites, both in plan view and with depth. We've also used some airborne radiometric data. Southwest England is blessed with a high resolution airborne radiometric survey. Also soil and stream geochemistry from the GBASE data set, a top of granite model that was actually generated in the 1980s, and some lineament data, which is essentially a proxy for faults, which I derived as part of my PhD. So machine learning in prospectivity has been around, you know, a fair while now. It's been sort of, it really took off in sort of 2014 onwards. And on the right, you can see a classification map, which is, you know, either there is mineralization or there isn't. So there is mineralization in the red areas, there isn't in the beige. That's not very useful because those are some significantly large areas that you would then go and have to follow up. But one thing you can do with classifications is look at the probability that that classification is correct. And that's what's happening on the map below, where you have a color scale where red is suddenly much more focused, going through orange to yellow into greens and blues, which are less prospective. And that's really useful. Rather than just having a 0 or a 1, it is or it isn't, you can start to get a better handle on how likely it is to be there. And machine learning in general is really useful, particularly with geoscience data sets, because geoscience data sets are often big. We can bring in large volumes of data, multiple variables, just as Jordan's just shown, can get lots of geochemical data. But we can also add in other things. The input variables can be non-Gaussian in distribution. And if you remember from school, a nice bell curve of probability, often in geoscience, the data doesn't look like that at all, and can be highly skewed. And the other aspect of that is that sometimes not all relationships in geoscience are linear. So it's not, if you've got 1 gold, it doesn't mean you've got 1 copper, for example. It might be that you've got 2 copper. And that's a non-linear relationship. If it then means that if you've got 2 gold, 4 copper, 3 gold, 9 copper. So that's starting to scale up quite significantly before, and it's a non-linear relationship. And one of the big advantage, particularly of the algorithm we're looking at today, which is the random forest algorithm, is that only a few known samples are required to train these machine learning algorithms. That's a bit of a controversial statement, because ideally you would want as many training samples as are required to be representative of the target variable that you're after, which, you know, in this case is mineralization. But equally, this random forest technique is really good at actually dealing with small data sets. So how do we go about doing this? This is sort of the simplistic model here. You know, you start with data, you identify your useful variables, you model it. That gives you a classified map. You make interpretations. That gives you knowledge. Hey ho, you've hopefully found a mineral deposit that you can go and follow up. With machine learning, it's perhaps a little bit more involved, and some of the steps under the hood are the things that people forget about. So data pre-processing is really important. Jordan also touched on some of this about cleaning your data, standardizing it. One big step that people miss out often is feature extraction. So just having a useful variable doesn't mean that it's actually in its best form. So feature extraction can enhance that. When you model, you can get your classification and do some intermediary metrics. And then there's sort of a feedback and interrogation loop here through testing that you've got something useful, evaluating the interpretations you've made and seeing if you can improve your overall workflow. And then you can say that you've got some genuine knowledge. So moving back towards data, for this study, I looked at a quick and easy data set to access, which is the BGS mineral occurrence database. I went with this because it's all readily digitized. We are blessed in Cornwall with other data sets that are fantastic, but they're all not as easily available, would require a lot more digitizing and plotting of where mineral deposits exist. So this is a quick way to get it. Unfortunately, it was a small data set, so there are only 34 tungsten occurrences in southwest England that are logged on the BGS mineral occurrence database. For machine learning, you need to split these into training and test samples. So all of our known samples, we call these true positives. We know they exist. These are split into 23 training samples and 11 validation samples. And because we didn't really care about anything else, all I did was generate some random samples to represent our true negatives. And so I generated the same amount of true negatives, 34. They're split the same. But also because they're random, I generated multiple sets of them and tested multiple times, because that gives you an idea of how the random effect is included in the model. We then did some feature extraction. In this case, I decided to use a fuzzy membership function, which is this equation here. It's not that complicated. Essentially, it's a normalization. What it means is that if your data looks like this black curve, which is highly unlikely, but it might do, you would essentially try and shift this curve to focus on something you're interested in. This might be, say, distance to faults, for example, or distance to lineaments in the case of this study. And you might shift it so that there's a certain weighting on a part of the data that you know is of interest. And you do this by changing the F1 data, which is the spread of the original data, and shifting spread of the new distribution, sorry, not the original distribution, the new distribution that you'll want to apply, and the F2, which is the midpoint, so the relative shift in where you would want to move this midpoint to. In this case, it's been shifted to the right slightly. And feature extraction essentially takes tungsten soil geochemistry data as shown in the figure, and you can start to play with it. And how you go about that is thinking about these guidelines, which is what data type do you have? So this is geochemistry data. It's a numeric data set. What's its target? This particular layer targets tungsten. And this is a point where you ask yourself, is that appropriate? Well, in this case, yes, because we're looking for tungsten mineralization. And you're also thinking back to that conceptual deposit model. How does it fit into that conceptual deposit model? The next step is really to enhance, combine, and validate your feature extraction. And this is what has happened in the step below. Essentially, we've combined our tungsten soil and our tungsten stream sediment geochemistry data. We've used the function fuzzy ore, which combines them. So either is it high, or is it high in one, or is it high in the other? We're combining both of them. So we're adding the two anomaly data sets together. And this is now, you'll see that the range has changed from pretty much 1 to pretty much 0. So here we've enhanced the data through our fuzzy membership. We've then combined it through fuzzy ore, and we're about to validate it. And validation is this idea that you can compare it to your known occurrences to see if it actually tallies. And we do this by using a receiver operating characteristics curve and calculating the area under curve. And you can do that repeated with different random sets to measure the random effect again. And this is essentially the model that gets produced. This is a probability map, And you can see that in general, we've hit a lot of the targets that we knew about. That's good. It means that the model's working. But we've also identified some areas of interest that we might want to follow up on. In terms of accuracy, this is where I start to question whether this model is good or not. Essentially, by doing our rock curve analysis multiple times, we've calculated that the probability, the mean accuracy of this random forest probability map is 0.989. Anything that's 1 is perfect. And you can see here the median score is 1. In machine learning, anything that's perfect is probably bad. In fact, you've probably done something wrong. I think the reason here is essentially that we've looked at these multiple times using a small amount of data. And this kind of feeds into what's called the bias-variance trade-off. And it's a horrible term because it's very confusing. So I'm going to rename this overfit and underfit. Ideally, if you look at this graph, we would look to go straight down the middle and try and minimize both overfitting and underfitting. We can't deal with this bottom bit, the noise. When you add together noise, underfit, and overfit, you get the total error. High variance in the model means that you've overfit it to the training data, and that's exactly what we've done here. However, that's not necessarily a bad thing because we're only looking for one target variable. Anything else we're not too worried about. The risk is that the training data we've used is quite small, so if there's anything that's wrong in it, we're going to get a really bad classification. But we've gone back and we've used this rock curve to make sure that our training data set is roughly representative of the anomalies that we're seeing, or actually vice versa. The anomalies we're seeing fit to the training data sets that we know about. And that's why this model is overfit and it has a really, really high accuracy. But don't trust the accuracy. There are other ways of looking at this. So if we go back to the model and look at those targets again, you can see that these are really broad. They're a lot better than perhaps what you might get from other approaches, but they're still quite broad targets and you might end up following up areas that are a waste of time. There are ways to go about this, and this is a method that I developed in my PhD. There's another thing called variance, which is why I renamed the other stuff. This is looking at class probability variance. So PC is just the map that we looked at before, and it's doing a little bit of math to work out what the variance is of, for other classes. In this case, it's a binary classification. So this is a really simple bit of maths. So we're looking for either one class or the other. It is mineralized or it's not mineralized. And then all we're doing is subtracting the variance from our original principal probability class to give this idea of a confidence. What that does is it completely refines the map. And now we're looking at some really focused targets. We're still hitting every single target we knew about. We're still cooking on gas here. This is good. But overall, we're still hitting those same targets that we want to go and follow up. But now we actually have some really specific information. And this is how you start to look at the accuracy of the model in a spatial context. Forget about that one single accuracy metric. The overall accuracy of 0.989 is completely redundant here. We don't actually care that much. And this is far more valuable. The blessing of being in Cornwall is that you can start to validate this even further with some of the historic data that I told you wasn't digitized. This is simply me flicking through a copy of Dines, which is the sort of the Bible to mineral exploration and mining in southwest England. And I found that there's several tungsten occurrences, either labeled as wolframite or non-economic metalliferous mineralization, which usually sits underneath tin in the descriptions. And with a bit of knowledge about the mineral system here, you can infer that is almost certainly wolframite. So this is starting to build up a really compelling picture. If we overlay both maps, you can start to see why you'd want to probably go and follow up on these areas. Interestingly, one of these sites that will remain nameless has been picked up by an exploration company. Variable importance. I think this is really worth digging into because it addresses that question of the black box that Jordan mentioned. I'm running out of time, so I'm not going to go into this too much, but you can argue this is a measure of what's biasing your model. Essentially, this is mean decreasing accuracy. So the tungsten here, the W, this is tungsten geochemistry. If you were to scramble that data set and make it random, the effect on the model would be a decrease in accuracy of about 85%. And that means that the model's really, really reliant on tungsten. That's fine because we're looking for tungsten. But there are some things in here that you might want to remove, such as this distance to line and rubidium geochemistry. The negative effect of mean decrease in accuracy is a double negative, which means that actually having these two data sets in means that the model is less accurate than it could be. This is opening the black box. It also can help you interpret what data you go and collect in your next round of exploration and save you money on your exploration campaign. I'm going to finish with this slide and just kind of sum up that essentially accuracy can be misleading. Don't rely on one metric. And then, check what influences the model, because bias exists, and check that bias variance trade-off and think about overfitting and underfitting with your accuracy metrics, because ultimately it's the spatial context of this classification that is of most value, and you can use this to appraise your exploration criteria, develop your exploration campaign, and build towards this mineral systems model. I will leave it there. Thank you very much.
Brilliant. Thank you, Chris, for a really interesting talk and for keeping it rather accessible in the large, other than the odd bit of maths. Even for someone like me, that was really, really interesting. I've got a couple of questions actually myself. If anybody else has any, please ping them into the chat. My first one is, how easily could this technique be applied to explore other metals in the Southwest?
I think it's very transferable. I think I've probably glazed over the amount of data preparation that went into this. There are a lot of tinkering with that initial feature extraction step to make sure that this all aligns. And I think, the data exists in Southwest England to do this. You could absolutely do this for tin. It's a much more complicated picture because the tin mineralization is so diverse in Southwest England. It's not as simple as you might initially expect. That's exactly the reason why I chose tungsten for my PhD, because tin was just too difficult to capture really in the time available, but it can be done. You could also quite happily do this for other base metals such as copper, zinc, probably lead, and I'd probably lump lead and silver into the same classification actually. So there's plenty of scope, but it's not a simple case of just transferring this method over. It would require careful thought, build up that mineral systems conceptual deposit model early on, and it might be a bit iterative at the same time because this did take a fair amount of care and thought that went in behind the scenes that I've glazed over.
Yeah, absolutely. I mean, I think that's quite visible. We've got another question from Ed. So obviously this is real data intensive stuff. So I mean, how effective would this approach be in a data poor terrain?
Yeah, good question. I think it's a really careful one to consider because it depends what you mean by data poor. If you've got lots of data but it's not very good, or there's a lot of questions around its accuracy in terms of how it's collected, your data will only be as good as what you put in. So I mentioned that bottom part of that graph that had the noise that I said you can't do anything about. That would be really quite high on an area like that. If you're talking more about where you don't have as much training data sets to rely on, so you're probably in a completely greenfield exploration area, there are other ways of generating training data. So you could do something very similar to what Jordan has applied, generate clusters, and then it's a bit of a dark art, but you can then make the argument that certain clusters may be mapping out appropriate training data. but that's quite a complex one. There are a few papers on that out there, which I'm happy to sort of have a chat to people about if they contact me directly. It is possible. It's far less straightforward than if you've got some known samples to work from, though.
Brilliant, thanks, Chris. And again, another question from John Fieldhouse. I'll read this out just in case people haven't got access to the chat. Hi, Chris. In terms of feeding in known deposits in the workflows described here, is there a significant danger in using deposits in directly analogous terrains, which are now tectonically separate and therefore subject to different weathering, erosional processes, etc., which could have an effect on geochemical data?
Yeah, I think that's certainly something that needs to be considered. It's probably one of the assumptions of the mineral systems idea is that you're looking for something that is based on, you know, what you've looked at in one place and trying to apply it elsewhere. And yeah, these places do exist in different areas. For example, if you were to try and find, even if you had pretty much the exact same terrain, so looking at, say, southwest England versus arguably the sort of southeast of Australia and into Tasmania, where there's similar mineral systems, even if they were identical in the way that they grew up and formed, the weathering, because of the different climate, would be very different. It would have an effect on the geochemistry. There are ways to kind of correct for different weathering profiles. At least there's some things you can do. There are some things you can't do, and sometimes that information is lost. But overall, I think you need to be a bit careful when you're completely changing environment as well. And that is perhaps an oversight of the mineral systems approach in some cases.
Brilliant. Thanks again, Chris. Okay, got one more here. And I'm aware that we've kind of just about crossed 10 a.m, so apologies, but really interested in exploring these questions with Chris. Thanks for joining anybody who has to scoot, but I think it's fair that we do a couple more questions. Chris, you mentioned saving time for exploration geologists and therefore money spent. But realistically, how does this machine learning method of initial grassroots exploration compare to more traditional methods? We're talking money, time, effort, reliability, extra. Are there any kind of indicators at this stage?
I'll be honest, it's a difficult one because it's very rare that exploration campaigns publish all of the finances alongside their exploration campaigns and where they spent the money. But to take an ideal example, if you were to say we had this mineral systems approach, we found a new grassroots area that we were very happy with based on what we've learnt in Cornwall, then the savings would theoretically be very high because we know what geochemistry we want to go and look at. There's a strong case to say that we probably don't need to worry about mapping fault lines initially. We could probably do without that data set in the first instance. And I would be of the opinion, if I was the head of exploration, to immediately order an airborne geophysical survey and get that early, which would not necessarily change the amount of money you spend overall, but it might change the amount of money you spend initially. The other side of that is that if I were to ask for an expense like an airborne survey, which is a big capital expenditure, my investors might tell me that they're not going to fund it. So it is a bit of a balance. I think in reality it doesn't quite work in that way. But I think if you had a long exploration campaign over several years, you could learn lessons and you could save money on perhaps being more focused in what geochemical elements you get analysed. You're probably unlikely to just you're not going to just drop your geochemistry campaign, but you might decide that you're going to only analyse for a handful of elements, which could overall save you more money in the long run.
Okay, interesting, brilliant. Cheers, Chris. Thanks ever so much, Chris. Thank you, Jordan. Thank you, everybody, for joining us. And yeah, we just hope that this session's really got the grey matter whirring this Tuesday morning, creating ideas for exciting research and innovation opportunities for businesses down here in Cornwall.